So up to this point, we've been talking about the limit and the fact that the limit doesn't care what's actually happening at the point of concern. So the limit as x approaches a doesn't care what's happening at x equals a. Now we want to connect those, all right? And the way we connect those is with the idea of continuity. So a very concise definition of continuity, in fact, this is really the definition of continuous at a point, says a function f of x is continuous at a if the limit as x approaches a of f of x equals f of a. Okay, so that really says that the limit value equals the function value. All right. So that's putting them together. Now it's easier to look at this as breaking it down into all the things that have to be required. So let's look further at that definition. Basically, that definition implies three necessary conditions. Okay. So the first one is that f of a exists, or in other words, that the function is defined at a. All right? So the function has to be defined there. The second says the limit as x approaches a of f of x exists. In other words, the limit exists at a. And then the statement from before is really the connection of those two. The limit value equals the function value at a. So basically, the reason we broke it down is because first you needed to really ensure that both of these exist on their own. And they could exist on their own and yet not be equal. So we're making sure that the function exists there, is defined there, the limit exists there, and that the two values coming from those first two are the same. Okay, so as with past things, we'll take a look at some graphical examples here to see when this might not be the case. Okay, so each one of these graphs here gives an example of basically when one of those conditions is violated and therefore the function does not end up being continuous. So it's not continuous at a. Okay, in the first one here, what we see is the whole at a, and so without any other point defined there, so f of x is not defined at a. So this really violates condition number 1. Therefore, without being defined there, it can't be continuous there. So it's not continuous at a. Okay, the next graph here, now, the function is defined at a. I can see that from the closed circle there. So 1 is okay. But remember, we've got this issue here where we've got the limit coming from the left and the limit coming from the right are not the same. So in this one, the limit as x approaches a of f of x does not exist. And that violates condition number 2. Okay. And, whoops, I'm sorry, this graph is incorrect here. Hold on one second. Okay, I've magically corrected that. So in this last graph here, we see the function is defined at a, and the limit going from both sides does seem to equal the same thing. So the limit exists and the function value exists. It's just that they're not the same. So the limit as x approaches a of f of x, which exists, does not equal f of a. So this violates condition number 3. Okay, so each of the previous is an example of a discontinuity at A. So a place which is not where the function is not continuous is called a discontinuity. But we have different levels of discontinuity. We have a removable discontinuity and a non-removable discontinuity. It's not that we actually remove them or not, it's just the potential. So it's a naming idea for the potential of really how severe the discontinuity is. So basically, a nice definition here of what removable or non-removable is kind of a game that you're asked to play. You're asked to look at the situation and say, if you had the chance to either define the function at one point or redefine the function at one point, could you make it continuous? If you can, it's removable. If you can't, it's non-removable. So we're saying here, a removable discontinuity is one where the function could be made continuous simply by defining or redefining the value of f of x at a. So the idea, and let's look at it through some graphs here. So in this first example here, let's call this f of x. Okay, so f of x obviously has a discontinuity at 2. So the idea is, I want to ask myself if I could basically define the function or redefine it. So either create a point or move a point, 1 point. Could you make it continuous? And the idea is, in f of x here, I could get rid of this there and instead define it there, and then hence I would make the function continuous. Not that I'm really doing it, but if I were allowed to, I could, and that makes this one removable. Discontinuity at x equals 2. All right, so let's go over to, let's call this one g of x. So g of x, notice I have a discontinuity at x equals 3 because there's an asymptote there. Essentially, that means the function is not defined there. But the problem is I can't just put a point anywhere. Anywhere I would try to put a point, it's not going to work. I can't go high enough to connect these because these go off to infinity. So there really isn't anything I can do. I can't make any change by using 1 point difference, a new point or a redefined point, to make this continuous. So as a result, this would be a non-removable discontinuity at x equals 3. Okay, but now you say, wait a minute, well, how am I going to know that if I don't have the graph? Well, notice what it comes down to. What we're seeing is, in the big difference between these two examples is the limit idea. In the one in f of x here, we had the limit existence, we just had the function defined at the wrong place. In g of x, the limit didn't exist. And that gives us a way of talking about this. So here's the key. For a discontinuity to be removable, the limit must exist. If not, the discontinuity is non-removable. Okay, so there you have a nice distinction. You have a discontinuity. If the limit exists there, but it has to do with the function value causing the discontinuity, then it's removable. If you have a discontinuity based on the limit not existing, can't be fixed, it's non-removable. All right. One further note, we've been talking about continuity at a point. Now we're going to want to talk about continuity over bigger intervals. The way we define that is really just saying that a function is continuous on an interval if it is continuous at every point in the interval. And again, that's something that we'll work on seeing.